Hello everyone. Today we are going to discuss the topic JK flip-flop. We will see the introduction. We will see the details of JK flip-flop and its applications. So, first of all, why we need to discuss this topic? If we look at SR flip-flop, it is unused or undetermined for the case when both the inputs are 1. When S equal to 1 and R equal to 1, the output is indeterminate. In the case of SR flip-flop, it is unused. To make that state useful, we go for JK flip-flop. So, what happens in JK flip-flop is when we give both the inputs as 1, the output simply toggles. 0 to 1 to 0, again 1, so on. 0, 1, 0, 1 continuous toggle take place, and that is what is shown here. Now rest of the table is similar to the SR flip-flop which we have seen in the previous lecture. Additional feature is when both the inputs are 1, the output simply toggles. And this is the symbol for the JK flip-flop. Now let us look at the functionality. So first case when both the inputs are zeros. Now we are looking at the case when both the inputs are zeros. To understand this better, let us look at how the NAND gate works. In the case of NAND gate, if the inputs are 0, 0, 0, 1, 1, 0, 1, 1, the corresponding outputs are, for the first case, it is 1, 1, 1 and 0. In simple words, when any of the input is 0, when any of the input is 0, the output is 1. Or we can say when both the inputs are 1, the output is 0. That is the situation in the case of a NAND gate. This is the situation in the case of a NAND gate. Okay. Now let us understand the JK flip-flop functionality based on the NAND gates. If we look at the circuit diagram, all we have is simply NAND gates. So understanding the functionality is enough to understand the functionality of JK flip-flop. So now when both the inputs are 0, according to this, the output is 1. So we have 1 here, we have 1 here. Now let us assume that the previous value in this case is 1 and now let us say this is 0. So let us see what happens. The 1 comes here. When the inputs are 1 and 1, the output is 0. So 1 and 1 gives us 0. So we have 0 here, and now because we have a 0 here, 1 and 0 gives us 1. So what is happening? Previous value was 1, new value is also 1. So what happens? The value is simply maintained. Whatever was the previous value, the same value is maintained. So it acts as memory. And that is what is reflected here. When both the inputs are zeros, the output is simply the same. The same state is maintained. So that was the first case. Now let us discuss the second case. Suppose we give 1 here and then we give 0 here. So when we give 1 here, 0 here, 0. According to the truth table, when any of the input is 0, the output is simply 1. So we get a 1 here. Then, now suppose this is 1. Suppose this is 1. Now let us see what happens. 1, 1 gives us 0. 1, 1 simply gives us 0. So that is the reason we have 0 here. Now this 0 reaches this point. So now we have 0. So we have a 1 here. So 1 is a stable state. Here the output is simply 1. And then here 0 is maintained. So actually what one can analyze is this is the only stable state that we can have for the JK flip-flop, when J is 1, K is 0, the output remains 1. So, that is the reason when J is 1, K is 0, the output is 1. Next, if we look at the structure, this is a symmetric structure. Along the x-axis, along the line which I have drawn, this is a symmetric structure. Now, because this is a symmetric structure, when we have given 1, 0, we got 0 here. So, if we give 0, 1, okay, when we gave 1, 0, we got a 1 here. So, if we give 0, 1, we are going to get a 0 there. So, if we give 0, 1, we are going to get a 0. Fine. So, if we understood this case, this is easily understood because it is a symmetric structure, and because of the symmetric structure, when we gave 1, 0, we got 1. So, if we give 0, 1, we are going to get 0. So, these three cases we have discussed. Now, let us discuss the last case. When both the inputs are 1. When both the inputs are 1. So, here, now let us assume we had a 0 here. Okay, so if we have a 0 here, the same point is connected here. So, we are going to get a 0 here. Now, one input is 0, so output will be 1. So, we may have a 1 here now. Then, again, this same point is joined here. So, we assume that we got a 0 there. So, 0 is now applied here. Now, what about 1, 0? 1, 0, the output is 1. 1, 0, the output is 1. Okay, fine so far. Now, this one propagates here. This one again propagates here. The same one propagates here. So, we are going to have 1 here. Now, this is valid for the case when the clock signal is actually 1. So, when the clock signal is 1, we have all ones, we are going to get a 0 here. Now, because of this 0 applied here, any one input is 0. So, the output according to this case is 1. So, now what is happening? This 0 is overwritten to 1. And one can further analyze that, okay, this 1 is again propagating in different places. And now, after analyzing, what you will find is, okay, again this will change to 0. And again it will change to 1, so on. Likewise here, this will change to 0, this will change to 1, this will change to 0. So, based on that analysis, what one can identify is, when both the inputs are 1, the output simply toggles. So, when both the inputs are 1, the output simply toggles 0 to 1, 0, 1, and so on. Now, the same thing can be represented in the form of graph, and this is called as timing diagram. So, here, what do we have the situation? When clock is high, J, okay, let us take this case, second case. When clock is high, J is 0, K is 1. When clock is high, here is the clock high, J is 0, K is 1. What about the output? Output is 0. So, what about the output? The output is 0, the second case. So, in this manner, one can represent the timing diagram from the truth table. So, now looking at the applications, JK flip-flop is used in counters. Counters require memory, and for the memory part, JK flip-flop can be used. Register. Register is nothing but collection of flip-flops. JK flip-flop we can combine together, for example, 8 JK flip-flops to get 8-bit register. They are also useful as frequency division. purpose. Let us see how. If you look at this diagram, if you look at, say, the frequency of clock signal, when we have two cycles, from here to here we have one cycle, and then from here to here we have another cycle. So for the case of two cycles, we have only one time period of the output. For two time periods of the clock signal, in this case, we have only one time period of the output. So what is happening? The time period here is getting multiplied by 2. If time period is getting multiplied, frequency will be divided. Hence, it is useful in frequency division circuits. So we have seen JK flip-flop in detail. We have seen the applications. That's all for today's lecture. Thank you.